So we really need to reiterate this point of endpoint versus equivalence point, because when we are conducting a titration, we optimally want the color change for the solution to sit at the equivalence point for the solution that we are titrating. So when we're looking at the pH range of our indicator, we ideally want the pKa of the solution to sit within this pH range. So a technique with titration, it's basically a technique which we're using to determine the concentration of the unknown solution. So we can either add an indicator to the solution we are titrating, we can add a pH meter, or we can do a combination of both. And so we're ultimately wanting to try to find the concentration of an unknown by finding the point at which the number of moles of the known solution are equal to the number of moles of the unknown solution. And so this is where we consider our equivalence point to be, and this is what we're going to then be measuring using our endpoint. And so remembering that our endpoint is going to be the point at which the pH changes, and so there'll be slightly more of one concentration than the other. And so when we're referring to the point at which the number of moles of the known solution are equal to the number of moles of the unknown solution, we're talking about the number of moles being the conjugated acid versus the number of moles of the original acid, or the number of moles of the conjugated base compared to the number of moles of the original base, and vice versa. So when we look at titration, we can consider what our titration setup would look like. So with our titration setup, this is what our typical titration setup would be. So we can see we need to have a stand in order to hold this all in place. And our main parts which we need is we need a flask and a burette, and then we need the tap on the burette. So in our flask, which we have at the bottom, so we'll need to have the burette suspended over the flask with the tap closed, and then this is using our frame which we have around it. And so in our flask, we're going to have the solution being titrated. And so the solution being titrated is going to be our solution of unknown concentration. So that's the solution which we want to be trying to find the concentration of. So this is what we call the analyte. It is the one which we are analyzing, and we want to find what the concentration of that is going to be. And so this is the one of it's an unknown concentration, but it is of a known volume. So we can't enable a titration to occur if we don't have a known volume of both our analyte and our titrant. So we would have our analyte in the bottom here at a known concentration. Then we've got our burette. And so the burette is like a measuring cylinder, but it's very, very accurately marked with volumes, because we need to make sure that we're putting in a very accurate amount of, and measuring very accurately the amount that we're putting in. And so the solution that we have inside the burette is what we call the titrant. So it's the one which is used to titrate the analyte. And so it's basically the burette is used to accurately measure the amount of the standard solution that's being dispensed into the solution of our unknown concentration. So the amount of titrant that is being dispensed into the analyte. And so the total standard solution being dispensed should be equal to the final burette reading minus the initial reading. So for example, say we start off with 50 mils of titrant in the burette, and then if the end point and the equivalence point is measured to be at 20 mils on the burette, then we can say 50 minus 20 is going to mean that we've had 30 mils of the titrant used. And so that would be the total amount of the standard solution, or the total amount of the titrant which has been dispensed. Then our standard solution, that's going to be a solution of known concentration, and then once it's been dispensed, it's going to be obviously a solution of known concentration as well. Then we've got the tap, and so the tap is used to accurately dispense the correct amount of the standard solution in order to neutralize the solution of unknown concentration. So we want to make sure that we're we open the tap and we close it as soon as the end point is, or the change in color is identified, so that it is the end point is as close to the equivalence point as possible, and hence we can get the most accurate results as possible. So we can consider different types of titrations. So an example which we've got here, so we can either have strong acid, strong base, strong acid, weak base, or weak acid, strong base. We can also have weak acid, weak base, but we don't need to consider those as they are very complex and outside of the realm of the syllabus. So first of all, we'll consider the concept of strong acid, strong base. So we can see with our strong acid, strong base titration, we've got the HCl as the analyte and the sodium hydroxide as the titrant. So we can see that as we titrate sodium hydroxide into the HCl, we're originally starting off at a low pH. And so as we progressively add more and more, we have a little bit of a buffer which occurs, but eventually we reach this point where the buffering can no longer counteract the addition of the sodium hydroxide. And so we have this sudden change in pH, where we have a very significant increase in pH. And so with a strong acid and strong base, we know that the equivalence point is going to be at pH of 7 or around 7, because the concentration of hydroxide ions will be approximately equal to the concentration of hydrogen ions. And this is because with a strong acid and a strong base, they both are assumed to dissociate to a full extent. So there should be a large amount of hydrogen ions produced when the hydrochloric acid dissociates, and a large amount of hydroxide ions produced. And we assume that those are about equal. Then, following from our equivalence point, because we've continued to add more sodium hydroxide beyond the equivalence point, we've then resulted in this eventual point where there is now more sodium hydroxide than there is HCl in the system, and so that's resulted in the pH then exceeding pH of 7 and plateauing around a pH of 12, indicating it's now a very basic solution. We can now contrast this with a weak acid, strong base titration, where we can see that we've got a weak acid such as acetic acid, and that's as the analyte, whereas we've still got sodium hydroxide as our strong base for the titrant. So we can see that we initially start off with a fairly low pH, but not as low as previously. And then as we begin to add the sodium hydroxide, there's a gradual increase in the pH, but we can see that there's a bit of buffering which is occurring because the sodium hydroxide is being added in small amounts, and so the acetic acid is able to counteract those effects with its buffering capacity. But eventually, there has been so much added that the capacity to buffer is exceeded, and then the equivalence point is reached. And so the equivalence point is reached at a pH of around 9. So we say that with weak acids and strong bases, the pH will be of the equivalence point and endpoint should be greater than 7. And this is because the concentration of hydroxide ions will be greater than the concentration of hydrogen ions, because we assume that the weak acid does not dissociate to a very large extent. In fact, it hardly dissociates, so there is very little H+ produced, compared with the sodium hydroxide, which dissociates to a larger extent, and so produces a lot more hydroxide ions because it's a lot stronger. And so that would be why the pH is then greater than 7. And so then we continue with our titration and we continue adding sodium hydroxide, and then we eventually exceed the equivalence point range, in which we then have the pH attain around a pH of 12, indicating that we've had further addition of the sodium hydroxide, or whatever that strong base may be. The final one we want to consider is a strong acid weak base. So with a strong acid weak base, we've got, starting off, we have a strong acid as our analyte, and then we've got a weak base as the titrant. So with the strong acid, we're originally starting at a very low pH, and as we begin to add the weak base, we can see that there's a little bit of buffering which occurs. However, this small amount of buffering is eventually exceeded because we've added so much base that the hydrochloric acid can no longer buffer. However, at this point, when we've added in so much of the weak base that it can no longer buffer anymore, we've still got a greater concentration of hydrogen ions than we do of hydroxide ions. And this is because the hydrochloric acid is stronger in how strong it is as an acid than the ammonia is in how strong it is as a base. So the concentration of hydrogen ions will be greater than the concentration of the hydroxide ions. And so this is because the extent of dissociation of the strong acid is very great, whilst the extent of dissociation of the weak acid is going to be very small. Hence, there is substantially more hydrogen ions than there is of hydroxide ions. And so when we consider that in pH, the greater the concentration of hydroxide ions, the greater the lesser the pH is going to be, and the greater the acidity will be. And so that means that the pH at the equivalence point and the end point is going to be less than 7. However, we continue to then add the weak base into the system, and so then eventually, after continual addition of the weak base, we eventually overwhelm the acid. No matter how strong it is, we eventually overwhelm the acid with so much base that we attain a pH that is now greater than 7. However, we can see that because it's a weak base, this pH is only around the pH of 10. It's not quite as strong. So in pH, we also need to make a very conscious note of the buffer region. And so this is because of our Henderson-Hasselbalch equation. And so where we say that pH equals pKa plus log of the conjugate base divided by its original acid. And so this basically tells us that at half the equivalence point, the concentration of the acid and the base are going to be equal. So therefore, the conjugate base divided by the conjugate acid concentrations is going to equal log in base 10 of 1, which is going to equal 0. So if we were to apply this to the Henderson-Hasselbalch equation, it would be the same as saying that pH equals pKa plus log in base 1 over 1, which would equal 0. So it would be the same as saying pH equals pKa plus 0. Hence, we can say that pH is going to be equal to pKa at half the equivalence point. And so this should be halfway between in the buffer region. So at halfway to the equivalence point, or in the case of this particular titration here, half the volume of the base being added, we can say that at half the amount of base being added to the equivalence point, we would have pH equals pKa, and hence the concentration of acid and conjugate base would be equal.